All right, our objective for today, I can simplify exponential expressions with fractional exponents. Read together, 1, 2, 3. I can simplify exponential expressions with fractional exponents. So, since we're already done with the easier stuff with, multiplication, division properties of exponents, now we're going to move into fractional exponents. Yay! Is it cold in here, or we're good? Or should we let it go? All right. So, we're showing exponential exponents, exponential expressions. Your Fourier model, you already know how to fill that in. I'm going to let you do that by yourself. It should look something like this, yes? However, I want you to write these steps down, though. It says, if the exponential expression has a fractional exponent, then rewrite as a radical and factor the number completely. Identify the index of the radical to find the root. Raise the power outside the parentheses and simplify. Copy that, please. All right. So previously, when I think it was from fifth grade. I think it was in fifth grade when you were introduced to square roots. Is that correct? You guys remember? No? Fourth or fifth grade. However, now that we're in algebra, we're no longer just going to see square roots. We're going to see nth root. We're going to keep building up. So instead of calling those symbols just square roots or whatever the case, we're going to call them a specific name. So for example, whenever you see the word radical, I want you to do this. Look up. That's the symbol for radical. You previously knew it as what? Square root, right? But since now we're going to be looking at other roots aside from square, that's why they're called radicals. So, to go over some of the terminology that we're going to need for this lesson, I'm going to write down here an expression. Look at this expression. This is square root of 16. The symbol, this one is called a radical. Radical. So have you guys heard like the server say radical, dude, right? That means they're talking about math. Never mind. Anyways, and the number that goes inside, it's called the radicand. Radical, radicand. Okay. Now, there's an invisible number here that you don't see. Do you guys see it? No, because you don't see it, right? It's invisible. That one's called the, look up, the index. And let me show you how it looks like in a different expression. I'm going to show you the cube root of 27. So look at this expression. The radical is a symbol, right? What is my index? 3. What is my radicand? 27. Does everybody see that? Okay. Now, the reason that I'm saying that in the past we saw these as square roots and you just focus on square roots because you were only in 2 dimensions. You were always doing stuff for squares or rectangles, right? So what does that mean? You're saying, Mr. Q, I just hear stuff. Let me show you. If I have a square, a perfect square, nice and straight like mine, and I said the area of the square is 16. What did I say? The area of the square. Is that correct? So what does that mean? That this area had to come from somewhere. So it needs a mom and a dad, right? It needs how many numbers? 2, and they have to be the same kind to give us 16. And that's how we say, oh, it's 4 times 4. So far, so good? So, well, guess what? Since now we're going to be looking at more dimensions or more roots, now we get into something like this. Look up, please. So how many roots are we looking for now? 3. Base, height, and depth. So what number times itself gives us 27? Let's see, 3 times 3, that's 9 times 3, that's 27. So the number is 3. That's why we're no longer going to say square roots, because that only belongs to squares. So now we're going to look at cubes, fourth roots, fifth roots, and so on. That's why we're going to look, now we're going to call them what? Radicals. Are we there? Radical. All right. So with that said, just to refreshing your memory, here goes some review from previous years. Prime numbers. We said that prime numbers are numbers. You don't have to copy this, just pay attention. Prime numbers are numbers that can only have factors of 1 and itself. What are factors? Two numbers that multiply. So let's see. Number 1. Number 1 is not considered a prime because 1 is already one of the factors. It has to be a different factor other than 1. So the next number that's a prime is 2. Because what are the factors of 2? 1 times 2. Are there any other factors that give us 2? No, unless it's decimals, but we're not looking at decimals. We're looking at whole numbers. How about 3? Is 3 a prime number? Yes, 1 times 3. How about 4? No, so if it's not a prime number, then it's a composite because it has factors of 1 in itself and others. 1 times 4 or 2 times 2. Everybody with me? How about 5? Prime, 1 times 5. How about 6? No, then it's a composite. 6 is 1 times 6 or 2 times 3. How about 7? Yes, 1 times 7. How about 8? It's a composite. 1 times 8, 2 times 4. How about 9? No, it's a composite. 1 times 9 or 3 times 3. About 10? No, this is 1 times 10 or 2 times 5. How about 11? Yes, 1 times 11. Those are the only factors. So those are prime numbers. These are composite. Any questions with that? Now remember these because we're going to use these first 5 prime in the next section. So now let me take you back to elementary school. In elementary school, your teacher say, okay, kids, today we're going to do factor trees. Yay. You guys remember that? And they're like, okay, copy this down. We're going to draw a tree. No, they didn't do that? They didn't do the factor tree with you guys? Oh, my bad. They didn't do a Christmas tree. All right. All right, never mind. So, to find prime factorization, this is how I show my students. You write your first 5 prime, 2, 3, 5, 7, 11. And then the first number that divides into 12 has to be one of these 5, the biggest number of these 5. Which is the biggest number of those 5 that divides into 12? 3 times 4. We circle the 3 because that's a prime number. How about the 4? 2 times 2. So my prime numbers are 3, 2, and 2. As soon as we multiply them, they're called prime factors because they're multiplying. And what does that mean? That if we multiply them, it gives us the original number. 3 times 2 is 6, times 2, that's 12. Are we there? So you practice. Find me the prime factorization of, somebody give me a number? 32. Find me the prime factorization of 32. Go. 30 seconds. Okay, let's see. 2 times 16, yes. 2 times 8. 2 times 4. 2 times 2. So my prime factors are 2 times 2 times 2 times 2 times 2. Yes? Because if you multiply them, it should give us 32. Yeah. Okay, if you did 4 times 8, you can, but then you're going to start 2 branches, right? But since we're going to go a little bit faster now, that's why I want you to start with one of the primes so that you only focus on going to one side of the branch. Does everybody understand that? Yeah. Or 2 to the 5th, that's fine, yeah. All right, we got this, right? Bless you. All right, so with that said, for today, we're going to look at fractional exponents. So I want you to write this down. Example Q. X to the 1/2 power Underneath that, x to the 1/3 power. Underneath that, x to the 1/4 power. Underneath that, x to the 1/5 power. Dot, dot, dot. Underneath that, x to the 1/23 power. That's right. You're going to leave a space here, draw a line down, and then you're going to write 9 to the 1/2. Let's write 8 to the 1/3. And then we're going to get 16 to the 1/4. And we'll hold on for right there. All right, so check this out. Since today there is no property, if you guys notice, there wasn't any property mentioned throughout the steps, but there is a process for fractional exponents. So pens down, eyes up here. Check this out. See if you see it. If you see it, don't say it out loud. Therefore, what would be the index on this one? 23. Does everybody see that? So the only one that does not have an index is which one? It's the 2. It's a square root, because we already know that square roots only have 2 numbers that multiply itself, right? Or a number that multiplies itself 2 times. So copy this, please, and then I'll go over it with numbers. Copy that. All right, let's see how it looks with numbers. This becomes what, according to this? Square root of 9. And what does that mean? What number times itself gives us 9? 3. This becomes, according to this pattern, is what? Cube root of 8, which means what number times itself 3 times give me 8? 2. Because 2 times 2 times 2 is 8. Does everybody understand what we're doing? Look at this one. This means that this 4th root of 16, what does that mean? What number times itself 4 times gives me 16? What is that number? 2. Copy that and see if you can do this one by yourself. 125 to the 1/3 power. Copy that and do that by yourself. Go. Very good. 125 to the 1/3 power becomes cube root of 125, which means what number times itself 3 times gives me 125? 5. Hands if you got that. Okay? So, those are the basics, and let's do some practice. Let's apply it to numbers. See how we do with that. Here we go. Copy these, please. We got example 1A and 1B. 1A says 343 to the 1/3, and B is 32 to the 1/5 plus 9 to the 1/2. So we're going to do this one together, just to make sure that we got these. So the first thing we need to rewrite this, is that correct? This becomes cube root of 343. And what does that mean? What number times itself 3 times gives us 343. And you're like, how do we do that, Mr. Q, with big numbers now? Well, this is where we practice our factoring. When in doubt, factor out. So we use the first 5 prime, 2, 3, 5, 7, 11. So let's see. Can 2 divide 343? No, so it's not 2. How about 3? No. How about 5? No, because it doesn't end on 0 or 5. And so it has to be 7 or 11. Could it be 11? So let's try 7. Does 7 fit into 34? How many times? 4. That's 4 times 7, that's 28. And how many more to get to 34? 6. You bring up the 3. So how many times does 7 fit into 63? 9. So 7 is our prime, and now we factor this one. What are the factors of this one? 7 and 7. Therefore, what number times itself 3 times gives me 343? 7. Copy that, please. That's how you use the factor tree for big numbers. When in doubt, factor out. Let's rewrite these over here. This is 5th root of 32 plus square root of 9. So, 5th root of 32, which means one number times itself 5 times, gives me 32. 2 plus, what is square root of 9? 3. 2 plus 3 is 5. Kind of, sort of? Was it a long weekend or what? Your brain is like slowly turning. Let's do a couple more. Here we go. Copy these. Example 1C and 1D. 1C is 81 to the 1/4. D is 121 to the 1/2 and 256 to the 1/4. See if you do those by yourself. Go. So first of all, we need to rewrite it. Is that correct? This is 4th root of 81, which means what number times itself 4 times gives me 81? Everyone? 3. Yeah, because 3 times 3 is 9. 9 times 9 is 81. When in doubt, factor it. If you don't see it, you're going to have to do the factor tree, right? All right. This one becomes square root of 121 plus 4th root of 256. So, what is square root of 121? 11 plus 4th root of 256. What number times itself 4 times gives me 256? Is it 4? 4 times 4 is 16. 16 times 16. Is it 256? Yes, it is. So this is 15. When in doubt, factor out. If you don't see it, you need to factor out the whole thing. Now, tomorrow we're going to continue with more practice of this, but there's one more thing that I needed to cover, look up as you're packing up. You're going to see in the home plate something like this. Watch. 8 to the 2/3. Notice that the numerator has a 2 instead of a 1. We can rewrite this as 1/3 times 2 on the exponent. Does everybody see that? Do we know how to do this first? That becomes what? Cube root of 8. And then at the end, we're going to raise that to the what power? So what is cube root of 8? 2 to the 2nd power becomes 4. Okay? Have a good one, guys. Enjoy your home play. Once again, today is going to be tutoring after school, so our home play is on page 35. Good one, everyone. Enjoy your home play. See you guys tomorrow.